We'll first of all look at the difference between alternating and direct current, then we'll look at the purpose of inverters and where they are used, then we'll move on and have a look at a simple example of how they work, and finally we'll look at a more advanced pulse width modulation example. So what is an inverter? Well, let's start at the basics first of all. So you probably know that there are two types of electrical power in use, which are direct current, or DC for short, which is supplied by batteries and solar panels, etc. Now this type of power is mainly used by small digital goods with circuit boards, etc. The other type of power is alternating current, or AC. Now this is supplied from the power sockets in your homes, and this will typically be used to power larger appliances. Both of these types of power have their uses and limitations, so we'll often need to convert between the two to maximize their use. An inverter is a device which is used to convert between direct current DC and alternating current AC. If you use an oscilloscope to look at the signal of these two types of power, you will see that direct current sits at its maximum voltage and continues in a straight line. That's because its current flows directly in only one direction, which is why it's called direct current. Think of it a bit like a river or a canal. It's always at its peak and it flows in just one direction. If you looked at alternating current, you'll see a wave-like pattern where the voltage alternates between its two peak voltages in both the positive half and then through to the negative half of its cycle. This is because the current travels back and forth. It's a bit like the tide of the ocean, where it reaches its maximum high tide and then transitions through to its maximum low tide, and in between the current of the seawater will flow and change direction. So an inverter simply converts from direct current DC to alternating current AC, and this is a very useful invention. You can also convert from AC to DC using a rectifier, and it's common to find both of these in some devices, and we'll actually look at this in just a moment also. So where are inverters used? Well, a common and fairly simple application of inverters is within solar panels or photovoltaic arrays, as these generate DC power, but the appliances in your home will use AC power, so this needs to be converted for it to be of any use. You can also buy portable inverters for your car, which allow you to use the car's battery to power small household appliances. A slightly more complex way they are used is when integrated into variable frequency drives or variable speed drives to control the speed, the torque and the direction of AC motors in order to achieve very precise control which saves energy. You'll find these on fans, pumps and compressors, and basically any equipment which rotates. They are used in all industries but extensively within HVAC systems for industrial and commercial properties. In this application, the inverter is coupled with a rectifier, and the AC power which comes in is converted to DC and then back to AC, but the controllers will change the frequency of the sine wave pattern. And by manipulating this, we can precisely control how the motor behaves. And when you join this to a fan or a compressor, etc., then you can precisely control how that performs also. This is partly how the Danfoss Optima Plus inverter condensing unit works. It has a very clever control loop which is measuring the cooling load and then changes the speed of the motor, which changes the speed of the scroll compressor, and that increases or decreases the cooling capacity to match the load, which results in precise temperature control as well as energy savings. So how do they work? Well, let's consider a simplified circuit where the DC source is being used to power an AC load, represented by the lamp. To convert the DC to AC, we will use 4 switches. We will pair the switches together so that switches 2 and 3 open when 1 and 4 close, and vice versa. This will allow us to force the current through the AC load in an alternating direction so that the lamp will experience an alternating current even though it's from a DC source. So let's give that a try. If we leave switches 2 and 3 closed and then open switches 1 and 4, this will cause the current to flow through the right hand side of the lamp. If we then close switches 1 and 4 and open switches 2 and 3, this will force the current to flow through the left hand side of the lamp. So you can see that there is a direct current source, but the lamp experiences an alternating current. The lamp will not see this as a sine wave, however, as the sudden switching will only result in a square wave. The sharp corners of the square wave can be damaging to electrical equipment, so we need a way to smooth the corners out. The switching is also far too fast for a human to do. If you consider the electricity you receive in the power sockets of your home, this will be supplied at 50 or 60 Hz depending on where in the world you are. This means that the current needs to reverse direction 50 or 60 times per second. So to achieve this, we'll use some special electronic components such as diodes, IGBTs, MOSFETs, etc. Now if you don't know how these components work, don't worry about that for now. We'll cover this in another video specifically for that. For now, just understand the circuits and how the current is controlled. Let's look at a three-phase example for a motor. You can see this circuit has a DC source and an AC load, and to convert the direct current into alternating current, there are a bunch of these IGBTs which are connected to a controller. The controller will send a signal to each IGBT telling it when to open and close. These IGBTs are paired together. So when the circuit is powered up, you can see that the controller is switching pairs of IGBTs to allow current to pass through them for a set amount of time so that the motor will experience an alternating current. In this example, the alternating current is in 3 phases. So this is used to power the motor, but how is it used to control the speed? Well, if we take a closer look at the IGBTs, we'll see that they actually open and close in a pulsating manner multiple times per cycle. This is known as pulse width modulation. What's happening is the cycle has been broken up into multiple smaller segments, and the controller tells the IGBTs how long to close for during each segment. I've shown how this works in just one cycle for one phase of the 3-phase circuit just to keep it as simple as possible. By opening and closing the switches at varying lengths of time during each segment of each cycle, the IGBTs can allow varying amounts of current to flow through the circuit and into the motor. The result of this is that the average power over each segment will result in a sine wave pattern. The more segments the cycle is broken into, the smoother the sine wave will be, and the closer it will mimic a real AC sine wave. So the motor will see the average value and will therefore experience a sine wave alternating current. The controller can then change the amount of time the IGBTs are open to increase or decrease the frequency and the wavelength to control the motor's speed, torque and direction. And with a few additional control loops, it can be used to exactly match the required loading to provide precise control of a system and unlock energy savings.